Okay. Well, welcome to the problem solving session for today. We have now solved my Zoom problems, um, and I hopefully can get things started faster next time. Yeah, I'll have to figure out how to do that for just having everything muted in the default settings. All right. So, heating curves. So last session, if you made it or not, or had a chance to watch the video, um, we just started talking about just this first step. So heating curves, you're just looking at we're just thinking about what happens as we take a system and we start adding heat to it, and the the expected thing to happen is the temperature increases, and that's exactly what we see until you get to the phase transition, and then things get a little bit weird because the temperature stops changing, and we can talk about why that is. Uh, but ultimately, all you're doing is you're sort of looking at you're trying to calculate. I mean, there's a lot of different ways, I guess, you can ask the question, but the kind of this one of the standard ways to do it is to say, I start with something like a block of ice, and I always use water, but and we also have some questions in the problem sets where you use carbon or something, but it's the same calculations. I start with a block of ice, and I, let's say, turn it into steam that's um, 150 degrees Celsius, and the block of ice, let's say, starts at minus 20 degrees Celsius. Um, oops. And let's say that you have 100 grams of ice here or something. You're converting it all to steam that's at 150 degrees Celsius. Um, the question you can ask about this, which I think is a question that's unlike the sum of chemistry, which is just like completely abstract, is not like a really difficult question to wrap your head around. It's just, if I want to take a certain amount of ice and I want to convert it to steam at a particular temperature, how much heat do I have to add to it? So if you're a chemical engineer, you can imagine this is probably something really common where you're trying to figure out exactly how much heat to add to a system to bring the temperature up or to convert it to steam. If you're, let's say, you're trying to design like some sort of power plant or something. Um, so that, yeah, I guess the nice part about this, even though it's kind of quantitative and there's definitely abstract components, is at least you have some familiarity with the things that we're dealing with. It's not, uh, you know, atoms and things you can't see, uh, or like chemicals that you have no familiarity with. I guess we are dealing with atoms. Okay, so when we looked at the first step for this, this is a different problem, but it's the same kind of idea. It was just how much heat is required to take an ice cube. We're saying how much heat is required to, can't see the question. Okay, sorry. The original question is just how much heat. So I have my iPad shared. Can you guys see the iPad? No, no, yes, no, yes, no, yes, no. Nope. We can't see writing. I'm not writing just yet. Can you see the little green cursor scrolling around? Okay. I see no on a lot of people's screen. I see a lot of no's. One capital O, capital letter no. Okay, so most people know. So you don't have to, a bunch of people are having trouble seeing it. Um, we can see when you write, but you can't see the previous notes. That's really weird. I don't even have any idea how to troubleshoot that. Let's just start from scratch then. So you guys can't, so you just see a blank page and then the new stuff that I've written. Can everybody see that? I see the old stuff. Some people can't see anything. Jesus. I wonder why that is. Oh, my sheet. I see. Hold on. I'm just a dummy and I maybe that's kind of harsh, but I fat fingered the screen share pausing. Awesome. All right. Now for real, hopefully we've hopefully solved all those Zoom problems. Um, all right. Let me reset one more time. Okay. There's nothing like troubleshooting things with like 100 and something people kind of waiting on you. Not that you guys aren't being super polite. It just adds to the general anxiety of the issue. All right. So starting over again. Um, Basically, what we're doing is we have some particular substance, we're feeding heat into the system, and we're looking at the temperature change. There's a lot of different ways to ask these questions, but a fairly standard way is to look at how the temperatures change. You guys are so nice. Um, how the temperature changes. So you say, okay, I'm starting at one temperature, I'm going to another. How much heat does that take? And that's sort of the question that we're asking here. And the other obvious thing to say is, I put so X amount of heat into a system, what's the temperature change that I observe? Ultimately, the way that you solve both those problems is extremely similar. So understanding conceptually what you're doing, I think, allows you to kind of access both of those. We're going in the direction of, I start at a particular temperature. Can I expand the screen or zoom in? And you guys are asking me for advanced stuff. I'm having trouble just getting the goddamn things going. I can zoom in some, but then I'm going to write the same size. So I don't know if that helps. In the middle of the zoom, it says view options. Landscape mode. There we go. Oh, good. Okay. All right. Y'all, all right. All right, we've got it. All right, so we're starting at minus 20 degrees. We've got an ice cube. Remember, this class is about chemistry, not Zoom troubleshooting, although it feels like that's really what it is, like teach Dr. Dredna how to use a computer. All right, so we're starting at minus 20. And like, in these examples, like in the big problems that we deal with, these get kind of long for an exam, but I think we've put a couple on there every now and again. We're going from minus 20 degrees and we're in an ice cube, and we're going all the way through all the different phase changes. And we're at 150 degrees Celsius, and now we're in steam. Okay, and we're starting out with some amount of ice there. And we're just trying to say, like, if we wanted to put this in a question form, we'd say, how much heat is required to, I don't know exactly like a real fancy way to write it, but to take a negative 20 degrees Celsius ice cube that weighs 100 grams and convert it to steam that's 150 degrees Celsius. And so this is where you just kind of, and this is really common in thermodynamics, we just kind of break things out into steps. And so that's what these heat curve type things are trying to show. So you've got, let's see, so your temperature will be on the vertical axis, and then you'll have heat that you're flowing into the system on the horizontal axis. And what you expect to see when you do these types of things is, I see things increase, and then they flatten out, increase, and they flatten out. Let's talk about that in a little more detail. So as I heat this thing, as I heat the ice cube, what I'm going to see is the ice cube is just going to increase in temperature, which is exactly what you would expect. If you had a thermometer and you've got an ice cube that's really, really cold at minus 20. So I think that's about what a normal, minus 20. I don't know what a standard freezer goes down to. It's pretty cold. But you have a temperature probe there. What do you expect to see as you start to heat it up? I'm going to see it climb, right? It's going to go minus 20, minus 10, etc. And then as it approaches 0 degrees Celsius, things start to get a little bit weird. So right here where we're hitting the phase change, 0 degrees is the freezing point slash melting point of water, we see that the temperature it just stops changing altogether. Um, this part is not particularly intuitive, at least to me. Um, and we'll talk about that. But so this is the phase change. This would be, we have all these silly names for them, but it's always the same stuff. Um, let's see. So we've got solid. Actually, my own cheat sheet for this, but yeah. So we've got solid. Now we're melting. I think some people call it delta H of melting, which is the easy thing to call it. But sometimes you'll see it called delta. I think more commonly it's called delta H of fusion. So at that particular part of the curve, it's going through this melting process. So this is actually, let's just, instead of me using the jargony stuff, let's just call that what it is. Scientists are really good at making things extra confusing. All right, so that's where it's melting. That's what's happening. So if all we're trying to do right now is just kind of establish what's going to happen as we go through this. We're not actually, I mean, we are going to solve this problem. And this is helpful for that, but we're just trying to qualitatively get what's going on. So I've got ice, I'm heating it up. The temperature increases. Then I hit where it's starting to melt. I've got my temperature probe in there. And now the temperature is not changing at all, but I am watching this ice cube. It's macroscopically what I'm seeing is this thing is melting in the liquid water. Finally, so at this point, it's both at the melting point, which is right here, it's simultaneously ice and water. And it continues to just convert from ice to water, ice to liquid water as I feed heat into the system. So as I kind of move in this direction, I'm getting, I have less solid ice and more liquid water. That's what I visually can see. But all I see on my temperature probe is that the temperature is just flat. It's at 0 degrees Celsius. So this is weird. And then once we get past melting, so I have no solid ice left, now I see that it starts to pick back up. The temperature picks back up. So now I'm in the liquid water zone. And then again, what happens when we get to 100 degrees Celsius up at the top? I'm sure my scale is a little off here. Because again, I see this thing flatten out. And then it stays flat as the liquid gets converted over to gas. So I have both phases there. That's when we actually give a normal name, it's vaporization. And then after we get through that, we see what the temperature pick up again. I'm really bad about drawing these all having the same slope, and that's not true. So now I'm at the gas. And then that'll just continue on, infinitely until, I don't know, at some point, I guess you can hit the temperature where like the gas, you start breaking bonds and stuff and you have a plasma. That would be like the next phase that you end up in. But that's not something that chemists typically worry about. That's something you might worry about if you were doing, I don't know if you guys are familiar with, they try to make these hot fusion reactors. They basically try to make something that works similar to the sun to get energy from. They've been trying to do that for like 100 years and they can never quite figure it out. But anyway, so that's what's going on there. So that's what you expect to see. So this is sort of, like if you can imagine yourself doing the actual experiment, which you could reasonably do at your house if you wanted to. Not that I'm saying anybody should go do this, but all you're doing is you're measuring the temperature as you heat this thing up. So you imagine you just put an ice cube on a burner, and I've got a pretty good temperature probe in there, and I'm measuring the temperature, and I'm taking points along the way here. And when I plot those and fit them, this is what I end up seeing. I see a rise in temperature, a flattening at the phase transition, and that just keeps happening over and over again. Yeah, so what the hell is going on here? So there's equations that we can use to describe each step along the way. But before we get into that, let's think a little bit about what's happening at the actual phase transitions, because that's kind of the confusing part for me. Actually, let's mainly think about that. Do we want to do the quantitative part, or do we want to talk conceptually? Let's talk a little bit about the conceptual part. So as I go, so we started out at minus 20 degrees Celsius. So here I'm just a solid, and I heat it, and now I'm at 0 degrees Celsius. And really what I'm at here is I have solid, but I also have liquid in equilibrium with one another. So the ice cube, I still have some ice there, and now I'm seeing a lot of liquid. And these two things are in equilibrium with one another. Yeah, nothing about that is particularly weird. I guess the strange thing is like, what the hell's going on with the temperature there? So what's happening with the temperature is, the way I like to visualize it is to look at these distributions. So remember, like the way we talk about this, like especially when we're dealing with thermodynamics, the way we talk about macroscopic variables is if it describes the system in its entirety. So when we talk about temperature, it's like, we've got this number 50 or I'm sorry, minus 20 or 0 degrees Celsius. And we're not using that. That doesn't describe the individual particles in the system very well. It describes sort of an average picture of them. Temperature is the average kinetic energy that we're looking at. It's not the actual kinetic energy of every particle in the system. So you can imagine that. So down here we have kinetic energy. And let's say that this point here, that I'm kind of highlighting in red, once you have a particle that has kinetic energy above this, it's increasing in this direction. Once you get beyond that red highlight line, that is where you become liquid. And below that kinetic energy line, you're a solid. Okay, so the kinetic energy is, how fast these atoms are kind of vibrating inside of that crystal. And if they vibrate fast enough, they can break their bonds, their intermolecular forces, and go from being a solid to a liquid. And we're putting that red line, we're saying if that's the kinetic energy that you need, it's sort of like the escape velocity if you're in a space shuttle for getting off the planet. That's the kinetic energy that we need to go from solid to liquid. Okay? When we're at minus 20, our distribution might look something like this. I'm just making this up, obviously, but it might look something like this. There's actually a tail here. So maybe there's a teeny tiny number of particles that can actually get to the liquid state. But it's not very much. We would take this top peak here and we would call this the temperature. That's what we're calling temperature. We're calling temperature the average kinetic energy there. It's sort of the maxima on this peak that's all kind of normally distributed to describe all the different particles in the system. There are some particles in the system that have lower kinetic energy, and there's some particles in the system that have higher kinetic energy, and then there's a small fraction of particles that actually has a high enough kinetic energy that they can become a liquid. As I start to increase the temperature from left to right, so like let's say let's say that this is minus 20 degrees Celsius. As I start to increase the temperature as I go from left to right, things start to broaden. I'm making this really dramatic, but now you can see that, let's say, I don't know, I'm just making this up, but let's say like we're getting really close now. So T is equal to minus 5 degrees Celsius. Now we start to see that, okay, more particles actually have enough energy to become liquid, but we're not at the melting point yet. It just, there's like a film of liquid water maybe that you see on the outside exterior of the ice cube or whatever. When we finally get to the melting point, this is when things start to get, I don't want to use the word interesting because I feel like it's an overuse of the word. I find it interesting, I guess. So maybe we can say that. So now we're like right here. So now what we see is that the average kinetic energy of the system is right on this interface between where the solid and the liquid are. Okay, So this is where things start to make sense as far as why the temperature is leveling off. So when we're on this, when we are down here, so when we're at t equals minus 20 or t equals minus 5, the average kinetic energy of the system is such that most of the particles in the system will be a solid. And as I put heat into the system, say going from minus 20 to minus 5, I'm shifting the average kinetic energy over, but the average kinetic energy of the system is still within that solid part of whatever, on this horizontal axis that I've drawn. When I actually hit this phase transition, the reason the temperature stops going up is because any heat that I put into the system is going to take a particle that's, it's going to take particles that are in this solid range and move them into the liquid range. So whereas before, and this is confusing, so try to wrap your head around it. So before, right, as I add heat to the system, what I'm doing is I'm increasing the average kinetic energy of the entire system. And that's what I'm measuring macroscopically as a temperature. Whereas now, as I add heat to the system, I can't have the average kinetic energy in the liquid zone, because what would that imply about it? That would mean that everything was liquid at that point. So if the average kinetic energy is higher, is so high that it's in this liquid region of this diagram that I've drawn, that means that the entire system is liquid. So every little bit of energy that I add just gives the particles more kinetic energy, but instead of the kinetic energy staying contained in the liquid, it actually goes into sort of ejecting these molecules in the gas phase. So another way to say that without using a graph is like at the phase transition, as I add heat to the bottom here, so I'm heating this thing up, you're still adding kinetic energy into the system in a sense. But instead of whereas before, that, I'm sorry, I forgot I was dealing with ice here. You're still adding kinetic energy to the system, whereas before it was making these things vibrate back and forth faster and faster and faster, which you could measure with a temperature probe. So that's what you're measuring there. You're measuring the vibrations in that ice crystal. Now, instead of the vibrations getting faster, an atom that was at one point part of the ice crystal now goes into being a liquid. And so that kinetic energy is kind of lost to the other phase. And so you can't actually detect that kinetic energy change within the ice cube. So that's what's happening there. So at the phase transition, all of the energy in the system is now going into converting it from solid ice to liquid. That's why we just don't observe an increase in the kinetic energy in the sense of like an average. We don't see a temperature change there. This falls out of the equations for this. So when you hit the phase transition, so at a phase transition, as I'm saying this stuff, I'm like, man, this is confusing. And even for me, like, my PhD is in organic chemistry. It takes a little while to kind of let all this stuff like settle and make sense. It wasn't immediately obvious when I first started teaching this course how all this stuff worked. But at a phase transition, the free energy of the system equals 0. Because we're at equilibrium. So whenever you're at equilibrium, delta G equals 0. It's kind of like saying whatever's going to happen for the system has already happened. Equilibrium is like, equilibrium is kind of what we're familiar with most things. Like you throw a ball up in the air, it's in a non-equilibrium state. It naturally becomes, it naturally falls down to the ground and finds its equilibrium state and stops changing. So equilibrium is when things have practically stopped changing, right? That's what we're saying at that situation. Let's see, I've got a question. For the number of particles, what does that pertain to? The vapor? So the number of particles is literally like the number of particles in the system. So, we've got 100 grams of ice here in our problem. And so, the number of particles is literally, if you went through it, we do this in like first semester, or maybe in high school chemistry, you did this, but if you went through and like converted that to moles and converted to actual number of molecules of water, the number of particles means, and I can actually just write that instead, number of molecules of water. And we're using that to describe the ice and the liquid, so sort of the entirety of the system, all 100 grams. Yeah, delta G is free energy. And when we talk about free energy, we're talking about, we're using that to kind of holistically describe what will or will not happen in the universe. If the free energy is 0, nothing will happen. If the free energy for the system is positive or negative, then the system is going to kind of move in one direction to try and become 0. Okay, so the free energy is 0. So at a phase transition, so practically speaking, what you're trying to wrap your head around here, because there's a lot, this is a lot. We're talking about thermodynamics. We're talking about, I've got what's called a Boltzmann distribution drawn up there. Practically what you want to remember from this is, like in a really hard, like I'm trying to do well in a test type situation, is temperature increases when I apply heat to any substance. And at the phase transitions, the temperature stops changing. And the reason it stops changing is because I'm at equilibrium. So the free energy equals 0. So this is important to remember, that delta G equals 0 for phase transitions. And we can look at a little bit of the math there. I'm trying to remember what we teach in the first semester. I'm bad about that. Do you guys know this equation? I think I asked this in office hour and the answer was, I think was yes. Either way, now we know it. So delta G for a system is delta H minus T delta S. This is like a super important equation in chemistry. This is at constant pressure, which is usually where we're at. The phase transition for energy. Okay, so yeah, what's interesting about this is that this is equal to 0. I'll let you guys out of here pretty well. If you want to hang out for office hours, you can. I'll stop this problem though, and we'll pick this up on Wednesday. And office hours are optional in the true sense of the word. But yeah, so if it's 0, what that implies, or what that tells us, doesn't imply, explicitly says, is that delta H is equal to T delta S. And so what's happening at the phase transition is that all of the delta H, which is the heat that we're adding to the system, goes directly into the entropy of the system. The temperature is constant, so we're not really worried about that. It's basically just saying that delta H essentially is being immediately used for entropy. So it's not an exactly correct way to think about it, but it's as if at the phase transition, you've broken all of the intermolecular forces inside of the solid ice cube. Again, not exactly true, or definitely not true, but it's an okay way to think about it. It's like all those intermolecular forces are broken, and now any additional heat that you're using to go into the system is strictly being spent on entropy as you go from the solid to the liquid state. Yeah, sorry, delta H and delta S. If you go back and look at the lectures that I posted on YouTube, it's in there. But H, remember, is enthalpy, which at constant pressure is essentially heat. And then S is entropy, which is a measure in some sense, not exactly, of disorder. And we usually talk about deltas, delta S, delta H, delta G, and that has to do with the type of variables these things are. But yeah, so it's like, I don't want to have to write it out, but it's all of, I'll write it out. All of the heat that enters the system, all the heat that goes into the system, it goes to entropy at the phase transition. So it's like, if before the phase transition, all we're doing is kind of increasing how fast these bonds are vibrating inside the ice crystal, at the phase transition, the energy is no longer going into those vibrations. It's kind of going directly into the entropy for this to convert it over into a liquid. I don't know. This stuff is confusing. As I'm saying it, I'm like, this sounds really confusing. Ultimately, you're just shoving heat into the system and kind of watching what happens. And there's a lot of different ways to kind of think about this microscopic picture. It's complicated, as you might expect, right? We're talking about things with atomic precision. Okay, so in our next class, where we have more time, we'll actually get into some of the calculations that we're doing. So, but this type of analysis that I'm doing for this, just this piece where we're going from solid to liquid, it holds for everything. Like it'll hold if you go and think about what's happening as you go from liquid to gas, it holds for that. And it holds in the opposite direction. So if I think about going from a liquid to a solid or from a gas to a liquid, it's the same thought process. So once you kind of get it for one phase transition in one piece of the heat curve, then you sort of have the entirety of it, right? So what we're going to add on next time is we're going to look at these two equations that we can use to do some calculations, which is Q equals mCp delta T, and also that Q is equal to delta H times, we'll try and stick to the mass if we can. So M is mass, C sub P is the heat capacity, Q is heat. What else do I have in there? And then delta H is the enthalpy of whatever phase transition we're looking at, which is a standardized number. But we can use these little pieces here to go through and do the calculations. So the calculations will tell you Q, and I know you guys are really good at plugging. I always say plugging, it makes it sound like derogatory, but I know you guys are good at like solving math problems. The powerful thing to kind of try to wrap your brain around here is trying to connect the quantitative part to this really kind of complex microscopic picture. That's what chemists really try to do. Anyway, all right, I'm gonna take a break so my voice can rest for a second. Plug and chug, baby. Yeah, I'm trying to do a better job of linking up the lectures with the session since I changed it kind of changed pretty quick. It was hard. Last night I spent some time doing it and then sent a message out at like 10 p.m., which I know is not helpful. Let me so for our next, I'll make an announcement. How about that? About what lectures would be useful, and I'll try and get out ahead to where you guys have more than just like, hey, 20 minutes before you know what lecture to watch, because I know you guys have a lot going on. But yeah, I'm trying to get the pacing right. It's a lot of content management. Anyway, all right, let me let my voice rest, and then when we go to office hours, that's a good time to ask about questions that are posted in like the extra practice problems or something. And if there are no questions, I have no problem. I'll just either make up a question or answer one of them. Anyway, all right, thank you guys. Yeah, the current schedule for exams is final. The schedule for the content may change throughout the semester. That just depends on how fast we go and how aggressive we want to be with learning.